Hello, everybody. My name is Masood Olia, and I'm a professor in the School of Engineering at Wentworth Institute of Technology. And I'm here with a problem I'm going to show you now related to the topic of stress concentration in axially loaded members. And this is one of the topics that I haven't had any videos so far on it. So I thought it's a good idea to have something on this important topic. So here we have a tapered plate with a constant thickness, as you can see, of 5 millimeters here, right? And it's so it goes from a width of kind of 40 millimeters to a width of 20 millimeters. So it's tapered, and then you also have a hole with a diameter of 20 millimeters. And this is, by the way, this R is called the fillet radius. Let me actually change the size of this. It's too thick. Okay, so that's called the fillet radius, and that also play a role in what the concentration is going to be. So first of all, the concept of stress concentration is that whenever there is a discontinuity in the material, be it a hole or the tapering where the cross-sectional area changes, as a result, the stress near the discontinuity, meaning somewhere here or somewhere here, is going to be larger than your average stress. Okay? So here what we have is basically, let me actually close my picture. So sorry, guys. I want to just get rid of this. Maybe put it somewhere here. Wait, yep, here we go. We got it. All right. So basically, it says if the allowable normal stress in the bar is 120 megapascal, right? That means you don't want the stress in this bar, anywhere in the bar, to be more than 120 megapascal, right? And then you want to determine the maximum axial force. So this load unknown here, right? So what is the maximum load that we can apply to this bar? Now, there is a factor called stress concentration factor denoted by K, and that's your maximum stress divided by what we call an average stress. This K value is determined based on charts. So depending on the size of the hole or the size of, or the way the tapering is done, you're going to have different stress concentrations. So basically, this is two cases. One, that we have to consider the hole, and then one case is considering this tapering that is done here. Okay, before I start the problem, let me show you that we have charts that will allow you to find the stress concentration due to the failure in the hole or due to the tapering of the bar. And see, these are the typically the diagrams that we use. Okay, so let me actually try to make this smaller, right? So basically, you need this value of 2R over W, and then you just, whatever that value is, 2R is what? 2R is the ratio of diameter to 2 times the radius divided by W. And then you can go and figure out the K value for it. And then also for the tapering is a little bit more involved. You're going to have basically two criteria here. One is the ratio of R over H, and then one is the ratio of W over H, which is the width of the this section to this section, right? And then you select the correct curve and the right value along the horizontal axis, and you go up and you hit the correct curve, and then you can figure out your K value. So let's get the problem started, okay? So what we want to do is go ahead. By the way, our maximum stress is the 120 megapascal. So what we can do is, based on the stress concentration factor, once with respect to the hole and once with respect to the tapering, then we can determine what the average stress is. Okay, so let's say if the failure happens in the hole, failure near the hole, okay? Or as a result of the hole, all right? So what do we need? You just saw in the charts below that in order to figure out the K value, the stress concentration, you need this ratio of 2R to W. W is this 40 and 2R is 20 millimeters, is the diameter. So 20 over 40 is 0.5. So that's all you need to find the K value. Let's go ahead and see what the K value is. So here we go, 0.5. Here we go. That's actually the maximum that we can get. So when you go here and you hit the curve, that falls exactly on 2.1. You see that? That's 2.1. So the K value is equal to 2.1. And let me show you what the K value is based on the failure due to tapering. So remember, for this one, you need actually the ratio. Let's take a look at it one more time. You need the ratio of R over H. R is this fillet radius here, and H is this the width of the smaller section. And then you need also the ratio of W to H. All right. So we come back here and say, okay, look, R over H is 10, right? It's 10 over, this is H, right? So that's 0.5. And then let's see, we also need the ratio of W to H. W is 40 and H is 20. So then we have to select the curve that has that ratio of 2. Let's see. Let me highlight this curve for you actually with the red. So W over H equal 2 is right here, actually. Let me see if I can draw that curve for you more or less. And what do we need? We said R over H here was what? 0.5. So let me use a different color here, maybe. How about that? 0.5, right? I'm going to go and hit that. And that falls right on 1.4. There we go. So we go across, you're going to see 1.4. So your K value now is 1.4 in this case. So this is going to give us a K value of 1.4. All right. So now we are ready to apply this concept of a stress concentration factor. So for the whole, remember, K is sigma max over sigma average, right? Therefore, sigma average is sigma max divided by K. So 120 over 2.1 for the whole. So that's about, let me see, 57.14. So your sigma average becomes 57.14 megapascal. So now, that's your sigma average. What is sigma average for an axially loaded member? It's load divided by area. But the question is, what is the area, guys? This is the tricky part. The area actually is the area of the weak section, not the area here. All right, the area of the weak section. And even in the chart, it shows you that the area is W minus 2R times T. Okay, so but basically you have to take the whole out, right? So you see W minus 2R then times T. So if you go ahead and solve for P, remember this is 57.14 megapascal means 10 to the power 6. So P becomes 57.14 times 10 to the 6 times the area. W is 0.40 millimeters. R is 2 millimeters, right? 20 millimeters rather, sorry. And the thickness is 5 millimeters. So now this is Pascal times meter square. So this is going to be in newtons. If you do the math, that's going to be about 5.71 kilonewtons if you divide it by 1,000. So this is the load needed if the failure is going to happen around the hole. Just the load needed that you reach a stress concentration factor of 2.1. Now let's do it based on the tapering. So based on tapering, what's going to happen? Based on tapering, remember K is 1.4 here, right? So we'll do it again, the same thing. Say sigma average is sigma max, which is 120 over 1.4. That becomes about 85.71 megapascal. And then we'll just say, okay, what is sigma average? Sigma average is load divided by area. Again, if you go to the chart, guys, look, the area that you're going to use is this cross-sectional area, not the cross-sectional area of the larger section. Always the weaker section. So it's H times T. H times T. Okay? So again, if you do, let me do that down here. So P becomes sigma average times H times T, right? So if you take the 85.71 megapascal, and which is 10 to the 6, by the way, right? You multiply it by area. H was 20, I believe, millimeters, and thickness was still 5 millimeters. This also comes out to be about 8.57 kilonewton. So of course, between these two loads, 5.71 kilonewton and 8.571 kilonewton, the maximum load that we can apply obviously is going to be the smaller of the two. So the maximum load that we can apply to this plate is going to be 5.71 kilonewtons. Guys, so as always, I appreciate if you like the video and subscribe to my channel. And I always come back with different videos on different topics. Again, thank you very much, and I'll see you soon.